Objective 12.5, Probability of Compound Events. In Objective 12.5, we want to be able to find the probabilities of unions and intersections of two events. We also want to be able to use complements as a way to find the probability of an event. So what do we mean by unions and intersections? Let's imagine that we have two events, event A and event B. And in my Venn diagram, each oval represents an event. So if I have a situation where I am interested in event A or event B happening, what that means is that I can have anything in this oval or anything in this oval happen, and it would count as an occurrence. Okay, now notice with these two circles I have this overlapping section. Okay, so we have dots over here representing possibilities. We have dots over here in B representing possibilities. We've got a few dots that seem to be both A and B. In order to have A or B, any one of these dots would count. And so you can see how both of these circles have been shaded in purple, because anything from either one of these would be an occurrence. And this is what we call the union of A and B. Put both of them together, anything from either one would count as an occurrence. If I'm looking at A and B, then I'm talking about just the intersection. I'm talking about just these three dots here that are in both the A oval and the B oval at the same time. So an intersection refers to looking for an event where it's A and B. Okay, only these three would count as occurrences in that case. Then we also have a situation called mutually exclusive events. And this happens when we have two events that have no intersection. There is no overlap like we see in these two cases. These two are completely separate events. There's absolutely no intersection. And so possibilities for event A are over here in this circle. Possibilities for event B are over here in this circle. There's no overlap. Okay? So let's keep that in mind now as we look at the probability of compound events. Compound events are when you're looking for the probability that A or B is going to happen. So in order to find the probability of A or B, which is the union, so that's the situation over here, we can take the probability that A will happen, so anything in this circle would count, plus the probability that B would happen, so anything in this circle would count. But notice when I take this circle and add this circle with it, these three right here in the overlap get counted twice. And we don't want them to be counted twice. They're each just single individual occurrences. So in order to get rid of the double up, we then have to subtract the probability of A and B. So this section right here, where we have the intersection, that probability needs to be subtracted because we've just double counted those when we counted them as part of A and when we then counted them as part of B. So this is the formula we need to follow when we are finding the probability of compound events, the probability of A or B happening. Take the probability of A plus the probability of B and then subtract the probability of A and B. So those in the overlapping area that got counted twice, we're subtracting one of those off. Now, the only thing that changes in that is if we have mutually exclusive events, because then there is no overlap. So if we're finding the probability of A or B when we have mutually exclusive events, all we have to do is take probability of A plus the probability of B, and that's it. There's no overlap that got counted twice, so there's nothing that has to be subtracted. All right, let's take a look at an example. So we have a card which is randomly selected from a standard deck of 52 cards. What is the probability that it is an ace or a face card? So it's a single card, but there's two different criteria that it could meet. It could be an ace or it could be a face card. So event A is a card that's an ace. Event B is a card that's a face card. Remember, that's the kings, the queens, the jacks. So, is there any overlap in these two events? In other words, is it possible that there are any cards that are both an ace and a face card? The answer is no. So, if there is no overlap, then that makes these two events mutually exclusive. And that means the formula I should use is the formula, the probability of ace or face equals the probability of getting an ace plus the probability of getting a face card. We don't need to subtract anything in this case because there's no overlap. So, how many cards are aces in the deck? Well, that would be 4 out of 52, so that's our probability of drawing an ace. Face cards are 12. So the probability of drawing a face card would be 12 out of 52, and therefore the probability of drawing either or is just the sum of those two, 16 over 52, which we can simplify to 4 over 13, or we can divide it out and get approximately 0.308. Okay, let's take a look at another example. This time we're drawing a card from the deck, and we want to know the probability that the card is a heart or a face card. So again, event A is the fact that our card would be a heart. Event B is that it's a face card. Do we have any overlap this time? In other words, are there any cards that are both hearts and a face card? This time the answer is yes. So because we do have overlap, we will need to use the basic compound event formula, where we take the probability of hearts plus the probability of face and then subtract the probability of the cards that are both a heart and a face. So, what's the probability of drawing a heart? Well, there are 13 hearts out of the 52 cards, so that's 13 over 52. Probability of drawing a face card is 12 over 52. And then how many cards are both hearts and faces? Well, that would be the king of hearts, the queen of hearts, and the jack of hearts. So that would be 3 over 52. By keeping my denominator the same all the way through the problem, it makes combining this much easier. Even though I could make this 1/4, I could make this 3 over 13. It's much easier to just keep that common denominator until the very end. So now if I take 13 plus 12 minus 3, I get 22. So 22 out of 52, which can simplify to 11 over 26, which gives us approximately 0.423 as a decimal. So I have a slightly greater chance of drawing a heart or a face card than I had of drawing an ace or a face card. Okay, now this is a situation where instead of trying to find A or B, I'm actually going to use the information to try to find A and B. So here's the example. A survey of 14 juniors here at Concordia found that 5 were taking U.S. history and 7 were taking American literature. 10 of the 14 were taking U.S. history or American literature. What is the probability that one of these 14 students chosen at random is taking both U.S. history and American literature? So our event A in this case would be that a student is taking U.S. history. Our event B would be that a student is taking American Lit. What we're trying to find is the and part. And obviously we have students who are taking both, or could be taking both. So we want to use the probability of A plus probability of B minus probability of A and B formula. But what we'll actually fill in is the probability of A or B, probability of A, probability of B, and probability of A and B is what we're going to solve for. So, probability that a student is taking A or B. Well, right here we're told 10 of the 14 were taking U.S. history or American Lit. So 10 out of 14 goes in that spot. Probability that they were taking U.S. history. Well, we were told 5 students were taking U.S. history, so that is going to be 5 out of 14. And the probability that a student is taking American Lit, well, we were told 7 were taking American Lit, so that's 7 out of 14. And so now if we make this our x, our variable that we want to solve for, we can combine the 5/14 with 7/14 to get 12/14, and then subtract that from this side, which would give us a negative 2/14. But then since we still have a negative here, we can divide both sides and end up with 2/14 or 1/7 as the probability of choosing a student that is in both U.S. history and American literature, which as a decimal is approximately 0.14. So we can still use this same equation to find the intersection if we already know what the union is. Now we also have something called complements in probability. And a complement happens when we have an event A. The complement of event A is all of the outcomes that are not A. So if I want to know, for example, what's the probability of not drawing a heart, that would be considered the complement of drawing a heart. Okay? So sometimes you can use this backwards thinking as a way to help you find probability. We note complements by using an apostrophe. So A apostrophe is read A prime, and it means the complement of event A. And we can find the probability of that by taking 1 minus the probability of A. So if I want the probability of not A, or the complement of A, then I can take 1 minus the probability of A to find it. Let me show you an example. When 2 6-sided dice are tossed, there are 36 possible outcomes, which are shown on your sheet in your guided notes. So let's say we want to find the probability that the sum is not 8. Well, this is a classic complement kind of problem. We're not trying to find the probability so much that something is happening, we're trying to find the probability that something is not happening. And so the easiest way to do that is to take 1 minus the probability that you do get an 8. So if you look on your paper and you count up all of the combinations that add up to an 8, you should find that there are 5 different possible ways to get a sum of 8. So the probability of getting an 8 is 5 over 36. That means the probability of not getting a sum of 8 would be 1 minus the 5 over 36, which would give you 31 over 36, or approximately 0.861. That is an example of a complement. Now we can also use complements when it's not quite so straightforward. as in part B. If we're asked for the probability that the sum is greater than or equal to 4. Well, when you look at all of the possibilities on your sheet, you can see there are lots of sums that are greater than or equal to 4. So instead of having to count so many different outcomes for what we want, let's use complements and count the outcomes that are not greater than or equal to 4. So that means 1 and 1, 2 and 1, 1 and 2, and that's it. Everything else gives you a sum that is either 4 or higher. So the probability of getting a sum less than 4 would be 3 over 36. If I take 1 minus that 3 over 36, then that will give me the probability of getting a sum greater than or equal to 4. So again, this is an example of using a complement, and that can be easier sometimes because sometimes the complement has fewer possible outcomes and it's easier to count them and use them to get our probability. The 33 over 36 would simplify to 11/12, and we would get approximately 0.917 as the decimal. So the chance of getting a sum greater than or equal to 4 is pretty good because this is a fairly high probability. All right, that's all there is to this lesson. Using your compound events formula and your complements to be able to find different probabilities for different situations. Make sure you complete the 12.5 quick quiz, which is the next step on the mentor mob. Then you can complete the 12.5 practice, and make sure when you're finished you get everything checked off by me. If you have any questions about using this kind of probability, don't hesitate to ask during our next class. We'll see you then.